Hi everyone, this is Professor Oaks, and in this video we are going to talk about parametric equations. So, if you look at this diagram below, you can imagine it as you can see here, as a particle that moves along the curve C. So this is the curve C, and obviously this is not a function, but you can maybe perhaps think of the coordinates of the the object or particle, as it mentions here, that it could be thought of as being functions of another variable. Let's just call it t. And so this other variable t right here, all right, the t is what we usually call a parameter, and then the f of t and the g of t, these are called parametric parametric equations. So that's what this section is all about. And then the c here, the curve itself, is called a parametric curve. Now, why are these functions of t? Well, it's t here as a generic third variable, but I will say that usually the functions are a function of time. So that's why t is usually the default variable name. All right, so now let's go ahead and look at an example here. So let's sketch and identify the curve defined by these parametric equations. So x equals t squared minus 2t, and y is equal to t plus 1. So this is x equals, think of it as f of t, and y is equal to g of t. So let's go ahead and sketch the curve here. So let's say that you have t, and then you have x, and then you have y. All right, so when you would normally plot a curve, you would just substitute values of say x and figure out what y is, but now we're going to substitute values of t and figure out what x and y are going to be. So if you have t is equal to 0, then x is, all right, so f of 0 is 0 squared minus 2 times 0, so 0, and y is g of 0, so that will be 0 plus 1 is 1. And then I'll just quickly go ahead and show you some other ones that you can verify on your own. So if t is 1, you have negative 1, 2. T is 2, you have 0, 3. If t is 3, you have 3, 4. If t is 4, you have 8, 5. And if t is, say, a 5, you have 15 and 6. All right, and then you could pick negative values for t if you would like. If t is, say, time, like I said, you wouldn't have negative time, but t is some other variable that it would stand for, then you might. So if t is negative 1, 3, 0, and if t is negative 2, 8, negative 1, and so on. So here is the sketch, and then we will verify and identify what this is after. So x, y. All right, so 0, 1. So 0, 1 is right here. Negative 1, 2. 0, 3. And 3, 4. So 3, 4. 8, 5. So 4, 5, 6, 7, 8, 5. And then 15, 6. Oh, do I want to go that far? Probably not. I'm not going to do that. All right, 3, 0. So 1, 2, 3, 0. And 8, negative 1. So 8, negative 1. And if I connect these, I hopefully can see that this is going to be a, here it is. This looks like it is going to be a parabola. Now, here is one thing that I will notice here, and forgive me for drawing that arrow right here. All right, you need to actually, if you go back and look at the original graph here, do you see how this graph, like the example graph here, had some arrows here? So these arrows point in the direction that t is increasing. All right, so if I look here, then my first point was when t was 0, 0, 0, 1, then I had negative 1, 2, so I'm going like this, then 0, 3, and then 3, 0, 3, and then 3, 4, and then 8, 5, so they seem to be going this way, all right, and even going from 3, 0 to 0, 1, when t is negative 1 to t is 0, I'm going this way along the parabola, all right, so technically it just keeps coming from this direction and then wrapping back around, all right? So keep that in mind that these arrows do matter as well. So another way to write this set of parametric equations is just as a system like this. X is t squared minus 2t, and y is equal to t plus 1. This is a parabola. And if you did not know that or were not comfortable identifying this, we can verify this by eliminating the parameter t. So this can be verified by eliminating the parameter of t. So t again is the parameter, so we can eliminate it. So if x is equal to t squared minus 2t, but y is equal to t plus 1, then that means that y minus 1 is equal to t, and I can substitute that in here. So what do I get? I have x is equal to, well, all right, y minus 1 squared minus 2 times y minus 1. So x will be y minus 1 times y minus 1. Let's distribute the negative 2. So negative 2y plus 2. I'll distribute the y minus 1 times y minus 1. So x is y squared minus 2y plus 1 minus 2y plus 2. And x will then be, if I simplify this, this will be y squared minus 4y plus 3, which is a parabola. Now, the one thing that you need to be very careful about is that this only tells me the shape of the curve and not the direction. So in order to find the direction, I only knew that by graphing this by looking at what direction the points are going in increasing order of t. All right, so that told me the direction. This only tells me the shape of the graph and not the direction. So again, this only tells the shape of the curve and not the direction. So these are both important pieces to know here. All right, what it looks like parametrically defined and non-parametrically defined. So now let's go ahead and try another example here. So in general, the curve with these parametric equations, x equals f of t and y equals g of t, where t is between a and b inclusive, so on the closed interval a to b here, then this has an initial point at f of a, g of a, and a terminal point at f of b, g of b. So if you looked at the last one, this really didn't tell us where the initial point and the terminal point were because we were looking on the open interval from, t could be any value, right? Negative infinity to infinity. But let's say you are looking at one like this, what curve is represented by the following parametric equations, and we're strictly on the interval from 0 to 2 pi. All right, so this means that a is 0 and b is 2 pi. And then as before, f of t is the x cosine of t, and g of t is the y, so sine of t. So now let's figure out what the initial point is. So the initial point is always going to be the f of a, g of a. So in this case, this is cosine of 0 and sine of 0. So that is 1, 0. And the terminal point is going to be, that will be f of b, g of b. So in this case, it will be cosine of 2 pi, sine of 2 pi, and then, all right, that will end up being 1, 0. So I see that the curve here sort of starts and stops at the same point, 1, 0. So that's not really helpful to me to know what is happening in between, right? So why don't I draw a table again, t, x, and y, and I pick some values between 0 and 2 pi, like 0, excuse me, and pi, and say pi, and 3 pi over 2, and 2 pi. All right, so the initial point was 1, 0, terminal point 1, 0. So in between, cosine of pi over 2, sine of pi over 2 gives me 0, 1. Cosine of pi, sine of pi gives me negative 1, 0. And then cosine of 3 pi over 2, sine of 3 pi over 2 gives me 0, negative 1. And so here is my sketch. It did not ask for a sketch, but if I wanted to, draw a sketch. Remember, it starts at 1, 0, and then it goes to 0, 0, 1, so 0, 1. So 0, 1 is up here, so make sure that you know that this is going in a counterclockwise direction, all right, so far. And then we have negative 1, 0, so negative 1, 0. So I'll draw the arrow to make sure that I, again, am sure of the direction that this is going. Then negative 1, 0, so negative 1, 0 is over here, and then back to 0, 1. So this clearly is a circle. So here's 0, the pi over 2, pi, 3 pi over 2, and back to 2 pi. All right, so now how would you actually figure out that this was a circle without graphing it? Well, I know that, all right, so I know, or it is known, that sine squared t plus cosine squared t is equal to 1, and sine of t with y, so that's y squared, and cosine of t was x, so that's x squared is equal to 1, and so x squared plus y squared equals 1 is a circle. There you go. What a time to be alive. All right, let's try another one. What curve is represented by the following parametric equation? So here you see the a is 0 and the b is 2 pi. So let's draw a table here. So t, x, and y. All right, so let's just try some values here. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. And if I do that and I substitute in the values for x and y, I have a 0, 1, which is my, again, that's called the initial point. And then I have a 1, 0, a 0, negative 1, a negative 1, 0, a 0, 1, a 1, 0, a 0, negative 1, a negative 1, 0, and a 0, 1. So that is a, what we call a terminal 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 point. All right, what a time to be alive, right? So again, here's my set of equations. It's x equals sine of 2t and y equals cosine of 2t. So if I go ahead and I draw a sketch here, I have my first point at 0, 1, the initial point, then 1, 0. And again, I want to keep track of which direction this is going to be going. All right, so if I start at 0, 1, and then go to 1, 0, then I'm going, in this case, I'm actually going what appears to be clockwise, then 0, negative 1. So 0, negative 1. So here we go, clockwise. Then negative 1, 0. That's over here. So here it is. And then back to 0, 1 again. And then I see that I go another time around. So this actually goes around this circle twice. So this goes around the circle twice. So if I want to eliminate the parameter just to see what this would look like, I'm going to use the same sort of trick as before. All right, so sine of squared of 2t plus cosine squared of 2t is 1. Well, this will end up being, well, since sine of 2t was x squared, and since cosine of 2t was y squared is equal to 1, which is a circle. But please remember that this equation here does not tell you, not in this case, not only does it not tell you the direction, but it does not tell you the number of revolutions either. So this is a circle, but this does not tell you the direction. So the THE, right? The direction or the number of revolutions. So all of this is important to get from the parametric equation. So try to remember this for the rest of your life. All right, so now let's try another one here. So let's try to find parametric equations for the circle with a center of HK and a radius of R. So the equation of a circle is x minus h squared plus y minus k squared is r squared. But if you recall then, right, just recall that we've been using this already. All right, so recall that cosine squared t plus sine squared t is equal to 1. And then in polar coordinates, all right, polar coordinates, x is r cosine of t and y is r sine of t. So what you really just need to do here then is just, well, all right, if you want this to be x squared plus y squared is equal to 1, well, then this is just a situation where if this is the x and this is the y, and you want to be x minus h and y minus k, then x minus h will be r cosine of t, and y minus k will be r sine of t. So then x will be h plus r cosine of t, and y will be k plus r sine of t. And there is my set of parametric equations. X is h plus r cosine of t, and y is k plus r sine of t. What a time to be alive. I really hope that you enjoyed that here and see another real life application of polar coordinates right there. All right, here is another one. Sketch the curve with parametric equations. X is equal to sine of t and y is equal to sine squared t. So now if I substitute this sine of t in for sine of t over here, I have y is equal to x squared. So the parametric equations, remember, the x equals sine of t and y equals sine squared of t. This tells you the direction of the curve. So this tells the direction of the curve. And then this equation over here, this will tell you that the shape of the curve is a parabola. So this tells that the shape of the curve is a parabola. All right. So I really hope that you're enjoying this here. So now, here we go. So it doesn't really tell us what values for t to use. So let's just go ahead and I'll pick a few values for t. Let me write that a little bit more nicely here so that you can actually, oh, bah humbug. All right, so there you go. So this whiteout was cheap as you can see here. So maybe I will try to get this whiteout to to be fixed here. Okay, so here is the whiteout being fixed. So we have t, and then we have an x. Remember that was sine of t, and we had a y, which is sine squared of t. So if t is, say, by the way, some values that you might want to pick are, you might want to say, well, okay, I want to pick 0 and I want to pick 1, but that might not be the wisest choice because these are trigonometric functions. You might still want to pick like pi over 2 and pi and 3 pi over 2 and 2 pi, all right? So if t is 0, you get 0, 0. If t is 1, you actually get 0.8415 and 0.7081 approximately. So that's not as easy to graph, all right? But if t is pi over 2, you get 1, 1. And if t is pi, 0, 0. And if t is 3 pi over 2, negative 1, 1. And if t is 2 pi, 0, 0. So let's go ahead and let's look at this. You see here that the 0, 0 is here more than once, right? So what is happening there? All right, what is happening? Why is that point repeating itself? Well, here's why. All right, so if x is sine of t, and you know that sine of t is between negative 1 and 1, and y is equal to sine squared of t, that means if I go ahead and I look at what's going on, that means that the y has to be, all right, between 0 and 1. So I can't have any y values that are greater than 1. So even though this here is y equals x squared, it's not the entire parabola. It's only the part of the parabola where y is between 0 and 1 and x is between negative 1 and 1. So if I start at 0, 0, and then I have 1, 1, so 1, 1, then I notice right here that I went this direction, right? And then I had to go back, and then I went back to 0, 0, and then over to negative 1, 1. So then over to negative 1, 1. So that way, and then back again. So this is what this graph looks like. It's going that way and then back and forth, back and forth, back and forth, back and forth, and it loops just along this part of the parabola. All right, so there you go. What a time to be alive. All right, let's try another one here. So let's move on to tangents here. So I really hope that you are enjoying this here. So here is the definition for tangents here. So this is sort of what you would expect given the chain rule, that dy dx is dy dt over dx dt. All right, and then for the second derivative, here is what we have here. So the second derivative is the derivative with respect to x of the first derivative. So that's d dt of dy dx over dx dt. So just be very careful about how this is all being written here. All right, so now let's go ahead and do an example here. So a curve C is defined by the parametric equations x equals t squared and y is equal to t to the third minus 3t. All right, so I hope that you're really enjoying this here. So here we have part A, show that C has two tangents at the point 3, 0, and find their equations. All right, so first, we need to find the slope of the tangent. All right, so first find the slope of the tangents. And so we know that, well, that will be the same thing as finding dy dx, but that will be, all right, so since we don't have a function in terms of just the x and the y here, we can do this implicitly as dy dt over dx dt. All right, so what is dy dt? So this is y, then dy dt is 3t squared minus 3. So we have 3t squared minus 3, and dx dt is, if this is x, is 2t. So that is the slope of the tangent. Now we need to find the, all right, the slope at the point of 3, 0, or x, y. So how are we going to do that? All right, so at the point 3, 0, so try to just remember that the real issue here is that we don't know what t is. We only know what x and y is, right? So we need to figure out what t is. So the one thing that we know is that t cannot be equal to 0, or this slope would be undefined here. So x was t squared, and y is t cubed minus 3t. So if x is 3, we have 3 is equal to t squared, so t is equal to plus or minus the square root of 3. And then here, all right, so if y is 0, and I factor this here into t times t squared minus 3, and then set each factor equal to 0, t is equal to 0, or t squared minus 3 equal to 0, I see that if I add the 3 here, I get that t is still plus or minus the square root of 3. But look here, I said that t could not be equal to 0. So what do I know here then? That t has to be the negative square root of 3 or square root of 3. So I just showed that C has two tangents at that point. One of them is when t is equal to the square root of 3, and the other one is when t is equal to the negative the square root of 3. All right, so now we need to figure out what those tangents are. So when the t is equal to the square root of 3, we have that dy dx is 3 times square root of 3 squared minus 3 over 2 square root of 3. And so then, well, square root of 3 squared is 3. So 3 times 3 minus 3 over 2 root 3. So that's 9 minus 3 is 6 over 2 root 3. So that's 3 over root 3, or just square root of 3. All right, when I rationalize the denominator there. And when t is equal to negative square root of 3, dy dx is 3 times negative square root of 3 squared minus 3 over 2 times negative square root of 3. So that will be 3 times 3 minus 3 all over negative 2 root 3. So if you look at this and do similar calculations, this is negative square root of 3. All right, so now what do you need to know? You just need to be able to find the tangents now, all right? So, well, okay, we'll just do that over here. So then let's find the equations of the tangent lines, all right? So now let's do step 3, find the equations of the tangents, all right? Or the tangent lines, all right? So then what do you have then? So one of them is, since one tangent is when the dy dx is equal to the square root of 3, we have y minus y1 is m times x minus x1. So the point was at 3, 0, right? So we have y minus 0 is square root of 3 times x minus 3, or y is square root of 3 times x minus 3. What a time to be alive. And the other tangent is, so the other tangent is when the dy dx is equal to negative square root of 3, and that's at 3, 0. So the same thing here, same similar process. So we have y minus 0 is actually negative square root of 3 times x minus 3. So y is negative root 3 times x minus 3. All right, what a time to be alive. There are the two tangents. So let's go ahead and move on to the next one today before we run out of time here. All right, there might be some new upload limit to YouTube or something that I don't know about, and they'll boot me right off of here. So find the points on C where the tangent is horizontal or vertical. So just remember that a horizontal tangent, this occurs when the slope, or dy dx, is equal to 0. So, well, all I need to do then is take the dy dx and set that equal to 0. So that was 3t squared minus 3 over 2t is equal to 0. And I really just need to see when the numerator is going to be equal to 0. So if I do that, then we just set the numerator equal to 0. So 3t squared minus 3 equals 0. And then I'll factor out the 3. 3 times t squared minus 1 is equal to 0. Set 3 times t plus 1, t minus 1 equals to 0. So then I divide by 3. So then I just have t plus 1 equals 0, t minus 1 equals 0. So t could be negative 1 or t could be 1. So then, since the x was t squared and the y was t cubed minus 3t, then when the t is equal to negative 1, I have that x is equal to 1 and y is equal to 2. And then when t is equal to 1, I have that x is equal to 1 and y is equal to negative 2. So that means that the points where there is a horizontal tangent, all right, so the points where there is a horizontal tangent are, right, and what are they? They are 1, 2, and they are 1, negative 2. So 1, 2, and 1, negative 2. All right, what a time to be alive. So now we need to move on and try to find the points on C where the tangent is vertical. And you might remember that I kind of already did this because I said that t could not be equal to 0 here, but we haven't found the actual point, just the t value where that would occur. So remember that a vertical tangent occurs when the dy dx is equal to an undefined value here. So to find this, we're going to set the set S-E-T. All right, there we go. Set the denominator equal to 0. So let me just fix that here. All right. So set the denominator equal to 0 here. So remember dy dx was equal to 2t to the second, or is it 3t to the second? 3t to the second minus 3 over 2t. So then 2t will be 0, t will be 0. And so at the point when t is equal to 0, so since, again, x was t squared and y was t cubed minus 2t, when t is equal to 0, we have x is 0 and y is 0. So therefore, the points where there is a vertical tangent, or point, because it's one point, right, is 0, 0. So when x is 0 and y is 0. And in this case, t also happens to be 0 at that point. All right, now, here is another part of the problem. So let's keep on rolling along, rolling. So determine where the curve is concave upward or downward. So remember that a curve is concave upward if the second derivative is greater than 0. And it is concave downward if the, all right, downward. Let me make sure that I spell this correctly for you. All right, I don't want any confusions here. All right, downward if the second derivative is less than 0. So for a parametric curve, the second derivative, d squared y dx squared, is d dt of dy dx all over dx dt, and that needs to be greater than 0 if we want it to be concave upward, or downward if this is going to be less than 0. All right, so just try to remember that that's what we are trying to figure out. Is this right here greater than 0 or less than 0? All right, so remember that the dy dx that we found before was 2t, or I keep on writing 2, but it's 3. 3t squared minus 3 over 2t. And the dy dt, which we don't actually need that, but the dy dt was 3t squared minus 3. And the dx dt is 2t. All right, so we need the derivative with respect to t of dy dx. So that will be d dt of 2t, I keep on writing 2, so 3t squared minus 3 all over 2t, and that's all over dx dt, which is 2t. So now for the numerator, I need the quotient rule. So just remember that you need the quotient rule to find the derivative of this numerator here. So that will give me in the numerator. All right, so that will be 2t times 6t minus 3t squared minus 3 times 2 all over 2t squared, and then over 2t, so over 2t. So now I can go ahead and simplify this here. So 2t times 6t is 12t squared. Then why don't I distribute this actually right here, if you look at it, is a negative 2 that needs to be distributed. So minus the 6t squared, and then plus 6, and then that will be all over. All right, 2t squared is actually 4t squared, then times 2t, that will end up being 8t to the third, so all over 8t to the third. Then 12t squared minus 6t squared is actually 6t squared, so 6t squared plus 6 all over 8t cubed. And then if I want to figure out where this is actually greater than 0 or less than 0, I need to first figure out where it is equal to 0, the critical number. All right, so the remember then what you're trying to do is figure out the points where the second derivative is equal to 0, because points where the second derivative, right, the second derivative or y double prime are equal to 0 are the possible points of inflection. All right, so then I need to see whether the graph is concave upward or downward on either side of that point of inflection. All right, so I just need to set the numerator equal to 0 here. So I'll factor out a 6. So 6 times t squared plus 1 is equal to 0. And then I will actually go ahead and oh, by the way, all right, the other thing that you want to remember is that those are points of inflection, but as I was getting ready to say here, it does not mean that the second derivative does not have any critical numbers here, because look at this. All right, here it is. If you look at the denominator, 8t to the third cannot equal 0. And so then if I look at this, then I can see that uh, the t cannot be equal to 0 here. Oh, by the way, I didn't actually finish this one. So t squared plus 1 is equal to 0. T squared is equal to negative 1. But I know that is non-real. All right. So the only critical number for the second derivative is t equals 0. So t equals 0 is a critical number for the second derivative here. All right, so here we go. So now let me go ahead and just write this over here as to what will be happening here. So if t is less than 0, what happens? And if t is greater than 0, what will happen here? All right, so then if t is less than 0, then the second derivative, and you can verify this for yourself by substituting in a value of t, but the second derivative is going to be less than 0, so this will be concave down. And if the second derivative is actually is going to be greater than 0 if t is greater than 0, and you can verify that again for yourself by substituting a value of t that is greater than 0. So that means here it will be concave up. All right, so now let's go ahead and try to sketch the curve. Remember that the curve was x is equal to t squared and y is equal to t cubed minus 3t. So what are we going to do here? All right, so here is the graph here. So remember that the tangent lines were, all right, so at 3, 0, at 1, 2, 3, 0, there was a tangent line, and they were, so at 3, 0, the tangents were the y is equal to square root of 3 x minus 3, and y is equal to negative square root of 3 times x minus 3. So then this will be square root of 3x minus 3 square root of 3 and square root of 3 negative square root of 3x plus 3 square root of 3. And the one thing that might help you graph this a little bit more easily is to know that 3 square root of 3 is about 5.2 and negative 3 square root of 3 is about negative 5.2. All right. So now let's go ahead and draw the intercepts for these lines. So one of them is at negative about 5.2. So 1, 2, 3, 4, 5.2. And so let me go ahead and draw this in right here. So there is my tangent line, and then the other one is at the 3 root 3's, so that's about 5.2. So 1, 2, 3, 4, 5.2. So here is the other one, right like this. All right, so I hope that again that you're really enjoying this. What a time to be alive, right? So go ahead and wake up and smell the roses or whatever you like to sniff. And then let's try to just remember that at where was it? Oh, the horizontal tangents were at where were they? They were at 1, 2, and 1, negative 2. So at 1, 2, and 1, negative 2, there were horizontal tangents. So right here, and right here, and at x equals 0, so where was it? 0, 0. So there was a vertical tangent at 0, 0. So here is 0, 0. Here is a vertical tangent here. All right. And now what I really need to do is just go ahead and graph this now. And if you think about what is going on, if I go ahead and pick like a, I don't know, what do you want to pick here? All right, so honestly, it doesn't matter because you know that this point right here, and this point right here, and this point right here, and this point right here have to be on the graph, right? So what is going on here? Well, I know that if I pick enough values that the graph is coming along here, right, from this direction, and then going through the point 3, 0, and then up to the point 1, 2, and then around to 0, 0, and then down to uh, 1, negative 2, and then back through 3, 0, and then back out this way, right? So that is the graph of this equation. All right, so again, make sure that you know what direction this is going, but it is, this does end up being the direction that it's going. So here is the graph of this curve. All right, now, by the way, I would like to at least think that this is not really a graph that you would be nearly as able to graph as easily without using parametric equations. So just keep that in mind as well. All right, so now let's try another one here. And this is just talking about the area. So here is the formula for the area when we're talking about the use of the parametric equation. So you can use this one, or you can use this one right here. All right, really, they're the same thing, by the way. So like, just remember that this one is from alpha to beta, or this one is from beta to alpha. So just try to remember that this is what's going on here. Okay, so the curve traced out by a point P on the circumference of a circle as the circle rolls along a straight line is called a cycloid. Find the area under one arch of this cycloid right here. So this is a cycloid, and this is the one arch of the cycloid that we want to find the area under. All right, so here we go. So the area is going to be the integral from a to b of y dx. So that's what it was. And then I know that I want this to be from, all right, now a is 0 and b is 2 pi r. So x equals 0 to 2 pi r of y dx. And now this will be equal to the integral from alpha to beta of g of t and f prime of t dt. And if you look here, all right, the y, all right, the y is going to be the 1 or r times 1 plus cosine of theta. And then I need to figure out what dx is going to be. And so if x is equal to r times theta minus sine of theta, then I see that dx is equal to, now here's the thing, which one is going to be the parameter? Is it the theta or is it the r? Well, it is indeed the theta, all right? And if you look at it, one way would be able to tell is because it's going from uh, theta equals 0 to theta equals 2 pi r. And so theta is some function that involves an r in it itself, all right, or is dependent on what the r is. So dx is going to be r times 1 minus cosine of theta d theta. So if I substitute that in right here, so this is the dx, what do I have? I have, well, all right, so I need to figure out what alpha and what the beta are, but since I'm just actually dealing with the well, well, by the way, let's just be really clear on what is going on here. All right, so here is what's going on here. If this is x and this is x, so since the x was r theta minus sine of theta, right? So if x is equal to 0, then I have 0 is r times theta minus sine of theta. Then I divide by r, so 0 is theta minus sine of theta. And then I have theta is equal to the sine of theta, so sine of theta is equal to theta. And I know that is true when theta is equal to 0, all right? So 0, so this is theta equals 0. And then similarly, if x is this 2 pi r, 2 pi r is r times theta minus sine of theta. So divide by r, so 2 pi is equal to theta minus sine of theta. And then I will go ahead and add the sine of theta here. So sine of theta plus 2 pi is equal to theta. So that means theta has to be equal to 2 pi. So this is going between 0 and 2 pi. All right, so now the g of t was the y here. So we have r times 1 minus cosine of theta. And then we had that the dx was going to be, dx was r times 1 minus cosine of theta d theta. So then if I simplify this here, I have integral from 0 to 2 pi, and r times r squared. So r squared times 1 minus cosine of theta squared d theta. And then because the r squared is a constant, I'm going to bring it in front of the integral. So I have r squared integral from 0 to 2 pi of 1 minus cosine of theta squared d theta. Now I need another piece of paper, so give me a second to locate this. I have to go chop down the tree right here. All right, so now that a tree is now down in my backyard, just so that I had a piece of paper for this video here, I will continue on with the problem here. So remember, I'll just rewrite it here. So it's r squared integral from 0 to 2 pi of 1 minus cosine of theta squared d theta. So I'll just write that down so that I don't have to keep on moving the paper back and forth on you. So I need to multiply this out here. All right, so let's go ahead and I will multiply this out. So that will be r squared, and then this 1 minus cosine of theta times 1 minus cosine of theta. So times the integral from 0 to 2 pi of 1 minus 2 cosine of theta plus cosine squared theta d theta. And then I will realize that I need to do each of these integrals separately. So which one will be the easiest? Well, all right, so we have the, well, well, okay, so we have r squared, and then the integral from 0 to 2 pi of d theta, then minus 2 integral from 0 to 2 pi of cosine of theta d theta, and then plus the integral from 0 to 2 pi of cosine squared theta d theta. And this one here is just integral of d theta theta. So this will be r squared times theta, evaluate it from 0 to 2 pi, and then minus 2 times the integral of the cosine of theta. That will be sine of theta, so sine of theta, and then that's evaluated from 0 to 2 pi. And then this other one, if you aren't as familiar with this, then you would need to probably go ahead and then try some other methods for evaluating that integral here. And that would be to rewrite this as integral from 0 to 2 pi of, well, use a trig identity here. So that's 1 plus cosine of 2 theta over 2 d theta. All right, so now what do we have here? Well, this is r squared, and then times 2 pi minus 0 minus the, all right, minus the, all right, minus the negative 2 sine of, well, all right, here, let's just put plus 2 pi, then minus negative 2 sine of 0, and then plus, all right, integral from 0 to 2 pi. So we'll break that up into a half plus cosine of 2 theta over 2. So integral of a half d theta is a half theta. And then for cosine of 2 theta over 2, we end up with 1/4 sine of 2 theta. So this part here will be evaluated from 0 to 2 pi. All right, so now if I go ahead and evaluate this here, then what do we have? I have r squared and then 2 pi and then plus, right, negative 2 times sine of 2 pi. So the sine of 2 pi, that will be, well, that will be 0, right? And then minus a negative 2 sine of 0, which is also 0. And then plus a half theta, so 1/2 times 2 pi plus 1/4 sine of 4 theta, and then minus the 1/2 times 0 plus 1/4 sine of 0. So then we have a half of 2 pi is actually pi. So we have r squared times 2 pi plus pi, then plus a fourth sine of 4, well, I said 4, that should be 4 pi, which is also 0, and then minus a half times 0 plus a fourth times sine of 0, which is 0. So then we just end up with 2 pi plus pi. So that's r squared times 3 pi, or just equal to 3 pi r squared. So that is the area of the, well, the space enclosed by one arch of the cycloid. So this shaded area right here, we just figured it out. The area was going to end up being, what did we say? It was 3 pi r squared. All right, what a time to be alive. All right, now let's go ahead and try another one. So if we want to find the arc length, so here is a theorem to find the arc length here. So find the arc length of one arch of the cycloid. X equals r times theta minus sine of theta, and y is equal to r times 1 minus cosine of theta. All right, so now let's see. Oh boy. All right, so actually this is the same cycloid that we just saw over here. All right, so I really hope that you enjoyed that cycloid, because we're about to use the same one again right here. So L, the arc length, is the integral from 0 to 2 pi, and then the square root of, all right, dx dt squared. And so since theta is the parameter in this problem and not t, right? Because I said, remember, that most of the time it would be t, but in this case we're investigating theta and not t. All right, so we need to figure out what the dx d theta is and the dr d theta is. So dx d theta is going to be, well, that is r times 1 minus cosine of theta, and dy d theta is going to be r times sine of theta. So again, you know what x is and you know what y is, and I think that you are a responsible enough party that you can figure out what the dx d theta and dy d theta are on your own. So now we have the square root of dx d theta squared. So r times 1 minus cosine of theta squared plus dy d theta squared. So r times sine of theta squared d theta. Now you cannot just take the square root of each term individually. Remember, that is not allowed. Like, that's not even possible. I don't know why you would think that. All right. So now I might make this either a little bit easier or a little bit harder. It depends on how you want to look at it, by distributing the r before or after I square all of this. But I'm just going to make this r squared times 1 minus cosine of theta squared then, and it's r squared times 1 minus cosine of theta times 1 minus cosine of theta, all right? So this will be equal to the integral from 0 to 2 pi of the square root of r squared times 1 minus 2 cosine of theta plus cosine squared theta. And then we have plus the r squared sine squared theta d theta. And just like how we have talked about arc length in the past, we want to try to get a perfect square under the square root so that the square root will go away. All right, so let's go ahead and try to just distribute the r squared here. So we have integral from 0 to 2 pi square root of r squared minus 2r squared cosine of theta plus r squared cosine squared theta plus r squared sine squared theta d theta. Then if I look at just this first, well, how about these first two terms and then these last two terms separately? So I'll factor out the r squared. So r squared times cosine squared theta plus sine squared theta. And cosine squared theta plus sine squared theta is equal to 1. So this is r squared times 1, which is just r squared. So then I will combine that with this r squared here. So r squared plus r squared is 2r squared. So I have integral 0 to 2 pi of the square root of 2r squared minus 2r squared cosine of theta d theta. And that's great news because I can factor out a 2r squared here. So 2r squared times 1 minus cosine of theta. And then if I know my trig identities, and remember, it's important to remember all of these for the rest of your life, all right? So then 1 minus cosine of theta, well, how do I want to deal with that then? Well, recall that sine squared theta is 1/2 times 1 minus cosine of 2 theta. And then if I just go ahead and I multiply by 2, 2 sine squared theta will be 1 minus cosine of 2 theta. And then if I want this to be theta and not 2 theta, then I really divide it the thetas by 2, right? So that got divided by 2. So this one needs to be divided by 2. So it's 2 sine squared of theta over 2. So that is what 1 minus cosine of theta is equal to. So now I have integral 0 to 2 pi square root of 2r squared. And then remember 1 minus cosine of theta was times 2. All right, sine squared of theta over 2 d theta. And now I can go ahead and just say, well, 2 times 2 here is 4. So I I I have integral 0 to 2 pi of 4 r squared sine squared of theta over 2 d theta. Right now, let me find another piece of paper before we scrunch too much all on the same page here. All right, so now if I take the square root here, I will have, what am I going to have? I am going to have the integral from 0 to 2 pi of 2r sine of theta over 2 d theta. And remember, I have not yet taken the integral yet, but since 2 and r are constants, I'm going to bring them in front of the integral. So I have 2r integral 0 to 2 pi sine of theta over 2 d theta. And then I can easily find this integral, all right? And so this will give me a 2r, and then the integral of sine of theta over 2 is negative cosine of theta over 2 times 2, so negative 2 cosine of theta over 2. And I'm going to evaluate this from 0 to 2 pi. So if I go ahead and I do this, well, all right, let's simplify this here. It's negative 4r cosine of theta over 2. And then if I evaluate this from 0 to 2 pi, I have negative 4r and then cosine of 2 pi over 2, all right, minus a negative 4r and cosine of 0. And then what do you have here? Well, all right, so cosine of the 2 pi over 2, or cosine of pi, is negative 1. So I have negative 4r times negative 1 minus a negative 4 times r times cosine of 0, which is 1. So we have 4r plus 4r, that's 8r. So all I'm telling you is that if you look back at our diagram that we started with of this cycloid here, where is the cycloid? I have no idea, but let me find the cycloid again, because this is very important here that we figure out what the cycloid looks like. So what I'm saying here is that the arc length right here of the cycloid, all right, the arc length, or the L here is equal to, what did we say it was? 8r. 8r. What a time to be alive. All right, so I really hope that you enjoyed this, and we're not done yet. All right, You better believe it. We're not done yet. So let me go ahead and find the last page that we're going to do here. All right, and this is sort of sad because it will be the last time that I will be making a video on a topic like this for a while, but I hope that you truly enjoyed this one here. All right, so we have the surface area. So here is the integral of that is going to give us the surface area, and then for parametric curves, just know that this is what we are going to use here. All right, so just try to remember this for the rest of our lives here. All right, so show that the surface area of a sphere of radius r is 4 pi r squared. Wow. How are we going to do that? Well, let's start with x is r cosine of t and y is r sine of t. All right, so then the dx dt is going to be negative r sine of t, and dy dt is going to be r cosine of t. So then let's follow the formula here. So s is going to be the integral from 0 to 2 pi of 2 pi, right, times the y, and the y is going to be the r sine of t, then the square root of the dx dt squared, so negative r sine of t squared, plus the r cosine of t squared dt. All right, that's it, right? Right? I mean, if we went ahead and we did this here, then let's look under the square root here. So we have r squared sine squared t plus r squared cosine squared t. So r squared times sine squared t plus cosine squared t. Well, sine squared t plus cosine squared t is 1, so we have r squared times 1, but this is under the square root. So the square root of this, square root of this, square root of this, square root of that is r. So if I come back here, I have integral from 0 to 2 pi of 2 pi times r sine of t times the r, all right, and that's dt. So then 2 pi times r is 2 pi r squared. So I'm going to bring the 2 pi r squared in front of the integral. So 2 pi r squared times the integral from 0 to 2 pi of sine of t dt. And the integral of sine of t dt, that will be negative cosine of t. And I'll evaluate this from 0 to 2 pi. So if I do that, we have 2 pi r squared times a negative cosine of 2 pi minus a negative cosine of 0. All right, so what is this going to give us? Well, all right, so that will be a, well, whew, all right. So, well, that will be 2 pi r squared times 1 plus 1. So that's 2 pi r squared times 2. So 4 pi r squared. So that is the surface area of a sphere of radius r. 4 pi r squared. What a time to be alive. I really hope that you enjoyed this section here on parametric equations, and I hope that you have a great rest of your day. What a time to be alive.